here's the situation. We're given the speed of a rocket, or the velocity in feet per second. Okay? So in other words, at 0 seconds, it's at 5 feet per second. At 80 seconds, it's at 49 feet per second. The first part says find the average acceleration. Ordinarily, to find the acceleration, you would find the instantaneous slope of velocity. And in fact, on the free response Thursday one, you're going to be asked to find the instantaneous acceleration. However, the function will be jagged there, so it turns out that you can't actually find it. But since I don't have a graph, I'm actually going to find just the average acceleration, which is the change in velocity over the change in time. It also asks to indicate units of measure. Now, before we even calculate, we can do that. Velocity is feet per second, and delta time is second, so the units will be feet per second squared. Okay, so the point I'm going to use is I'm going to use 0, 5, and I'm going to use 80, 49. So to find the acceleration, you're going to go 49 minus 5 over 80 minus 0, whatever that is, feet per second squared. The next part, there's a lot of things being asked. It says, using correct units, explain the meaning of this. Obviously, when you integrate velocity, you get distance or displacement. So I'll say this is displacement, specifically of the rocket from t equals 0 to 80. Okay, so in other words, that's how much further the rocket has moved in that time. And it says, use a midpoint Riemann sum with 3 subintervals. So here I split it up into 3 subintervals. The integral is obviously asking for the area under the curve, but we're asking for a midpoint. So a midway between 10 and 30 is 20, and if you look, 20 has a height of 22. The next part in between 30 and 50 would be 40, and if you look, it has a height of 35. And then very lastly, between 50 and 70 would be 60, and it has a height of 44. So if you look at the first rectangle, right here, its base is going to be 20. Its height is 22. If you look at the next rectangle, which is given by this height, its base is still 20, and its height is 35. Okay, and lastly, if you look at the last rectangle, okay, its base is still 20, its height is 44. So whatever that comes out to be is your approximate integral. On the free response Thursday, it's not going to be a table, but an actual graph, and you can use geometry to find the area. The next part says there's a rocket B that's launched with this acceleration, and you know that the initial height of the rocket is 0 and the initial velocity is 2. That's going to be very important. And it says, which of the 2 rockets is traveling faster? Well, we know rocket A already. We know the velocity of rocket A at 80 seconds is 49 feet per second. Now, how do I get rocket B? Well, I'm going to integrate the acceleration. More specifically, I'm going to integrate it from 0 to 80. And what that'll give me is not just the velocity, but more specifically the velocity of rocket B from at time equal 80 minus the velocity of rocket B at time equals 0 by the first fundamental theorem of calculus. Okay? And what you can show, either by hand or by calculator, is that this integral is going to be 48. Okay? Velocity of rocket B at 80 is what we're looking for. And then the velocity of rocket B at 0 is 2 feet per second. Okay? So when you add 2, you get that the velocity of rocket B at 80 is actually 50, which is greater than the velocity of rocket A at 80. So rocket B is traveling faster for this very reason.